Okay. Good afternoon. I think it is time to start now. I welcome you to the class of numerical optimization. And I want to tell you that this class is an experiment. It's the first time we give this course here in Freiburg. And it is a mix of different faculties, which makes it particularly interesting for me. So maybe I start by introducing myself. My name is Moritz Diehl. I am a professor at the Department of Microsystems Engineering at the engineering faculty of this university. You know, the engineering faculty for the mathematicians is 10 minutes by bike from here at the airport, Flugplatz. At the same time, I'm affiliated to the Department of Mathematics, which is located here on this campus. And the aim of this lecture is to mix students from computer science, from engineering, which are in Flugplatz, and from mathematics and possibly physics or other subjects which are more located here. So you might think this is quite experimental because you have different backgrounds. On the other hand, I'm also very confident that this will be a success. And the reason for this is, first of all, that I have 8 years experience teaching nearly the same class. I taught it at a different university, at KU Leuven, to a Master of Mathematical Engineering. So mathematical engineering is students that have this mix that we have present here. This class will actually require 3 sets of skills and will actually train each of you in the complementary set of these skills. So what we will do, of course, what you would expect here is mathematical theory, right? So one topic is for sure mathematical theory. There will be a proof from time to time. And that's the main part of the things and the contents that we cover during this lecture part of the lecture. I just realized some people arrive a bit later. Good, we come to that later. So mathematics is one part, but the other part is also programming. So we will do some form of programming in this lecture, because we don't want to do the mathematics just on paper, but we want to make the mathematics run and move and do things for us, because that's what optimization is all about. Yeah? So we will also do programming. I should say in a basic form, we will nearly exclusively use an environment that's called MATLAB. And that is quite easy to start with. It's an interpreter language, basically, with very immediate cycles from typing to seeing something. So that's the second part. And I guess that some of you are better in this than in mathematical theory and the other way around. And then the last part is also, there is always a bit of modeling and transfer from a real world to the mathematical world. I call that modeling. And that is also a bit of part of this lecture. And that's where typically engineers are a bit better trained in. This is not the main focus, so they are ordered in priority. Mathematical theory is the main topic of this lecture. Programming is very important in the exercises in particular, and modeling can become important in particular in the projects that we want to do at the end. So now I introduced myself briefly. I said where I am. I just want to tell you that I studied mathematics and physics in Heidelberg University, did a PhD in mathematics, then became a professor in engineering in Leuven, and now I'm a professor of engineering with an affiliation in mathematics here in Freiburg. So now I want to learn a bit about you before we start with the motivation and the introduction of this course. So to get really an idea if you are from as diverse backgrounds as I hope, let me say I hope it, because it can also be a synergy. I want to ask first, who is a mathematician, who studies mathematics? That's a considerable part of the course, which makes me very happy. You are the main audience, as you see from this campus choice already. So if it gets boring to you or not the right level or something, you should give immediate feedback. Yeah? But it doesn't mean that the other people don't know some things better than you do. So let me ask, who is a computer scientist? So it's still nearly an equally sized group. So computer scientists had the same mathematics as you and as engineers in the bachelor, or a bit the same, but had been more training in programming. There are, of course, also engineers, I guess. So who is an engineer in some form or the other? Engineers like microsystems or embedded systems engineering. So a slightly smaller group, but still significant enough. And I should say, some of the students of engineering asked me to record this lecture because they couldn't attend, so there might be a few more engineers watching remotely because we record this lecture and put the videos online. This is also an offer that you can have, of course. I just wanted to tell you that's the reason why we have a camera in the back. Yeah, so we all are interested in optimization, otherwise we wouldn't be here. I'm particularly interested in solving optimization problems. That's the main topic of this lecture. But before we solve them, we need to know what they are good for. So I would like to have a bit of an introduction around where we see what do we actually need optimization for. And then I want to also talk about the organization of this course in some more detail. But before we start, as I said, there is optimization everywhere, and I want to start by saying that usually where optimization starts is where simulation ends. Yeah? So usually a lot of engineers, a lot of scientists have simulation models. So wherever you simulate, you have some computer models that allow you to predict something, to play with parameters, to change things, and to see if they really do what you want in the virtual world. That's what simulation is all about, and I would say that all forms of engineering, of sciences, are now 95% of this time. People sit in front of a computer and just simulate. I think this is not exaggerated. Yeah? So, to get an idea, did any of you at some point sit in front of a computer and play with a simulation program, or maybe you had to do it in the studies or during an internship, so where you took something like you wanted to simulate, I don't know, the motion of some robot, or you wanted to simulate an electric circuit, or you simulated maybe a chemical plant or something like the Earth's atmosphere. You can simulate a lot of things. And just to get an idea, did you already have exposure to simulation, which is, I would say, what most engineers and most scientists do when they are professional, but maybe not in the studies? So who has ever run on a computer some form of simulation program? Mm-hmm. So significant enough, but it's justified to talk a bit more about this. Yeah? So simulation, probably who of the mathematicians or those that didn't do simulation, who has ever had a course on ordinary differential equations, for example? Not so many. Okay. Ordinary differential equations usually just are to simulate. And who had a course on partial differential equations? Even less, but that's also about simulation. It's numerics very often of partial differential equations. So it's always a simulation which we do a lot. And when you simulate, what we do is actually we take our simulation model, we sit in front of the screen, and then we say, okay, let's experiment and try change something, maybe make the electrical circuit a bit bigger and see if it still has a nice behavior or maybe a nicer behavior, and so we play with it. And at the end, we are happy, and then we say to the boss of the company, we have developed the system, I think you should build that, right? Or you say, we were able to actually predict the weather or something. Tomorrow there will be rain. Yeah? This is already a bit different. You see maybe the difference? In one case we wanted to design something, in the other case we wanted to actually predict something. But if we predict something, there is some other thing actually that you do and that is actually done. You have to first understand in which state you are. So if you have a weather prediction, you will have to observe the world and then try to understand in which state are we, and then only you can predict. And how do you actually find out in which state you are? You do that also by somehow plotting. I mean, climate scientists do that. They look at a model, they make some assumptions, then they simulate the trajectories, and then they take samples from ice, for example, and look at CO2 levels over the last millions of years, and then they try to fit their models by adapting model parameters or making different assumptions until they say, this is a good model. And then they tell us, yeah, by the end of this century, probably you will have an increase of the global temperature by 3 degrees. Yeah? So what I wanted to stress here is at some point they have a simulation model and they play with something and compare it with something. And that is not so different than what the engineer who designs something does with the simulation model. You play with the inputs of a model in order to see what comes out of it. Yeah? So we call this a forward model, because you have inputs that you play with, and forward model. And you see what comes out in some form or the other. And as if you think about these two tasks, estimation is one of them, the other is optimization. There are many other tasks that you can do with simulation models, of course, but many of them are actually implicitly optimization problems. So what we actually want to do is we want, for example, to find the circuit which has the smallest surface on a chip, but still meets our specifications, for example. Yeah? So these could be specifications, which are more or less the things that you usually get at the end of a simulation. So these are outputs. Yeah? So a forward model takes inputs and creates outputs. Here you have the inputs. Here we have the outputs. And then you can compare them. But what you really want to do is actually to start with the specifications, and then the computer could tell you what are the necessary inputs for that. For example, when you have an estimation problem in climate science, you could take the trajectory of the past. You could take your simulation model. You could say, these parameters are not determined. I don't know them perfectly. Please adapt them so that it fits the past as good as possible in some form. So we have to invent an objective function, but after we have invented that, we can formulate at least our problem, and then we are at an optimization problem. So simulation ends where optimization starts, I would say. Or even better, we should say that simulation is an integral part of optimization, because you cannot optimize without simulating, so to say. Yeah? And so what optimization does, it starts from requirements in some form or the other, from requirements to the inputs. And these are these inputs. Yeah, so the inputs of some simulation model are the things that we are trying to find. We are not interested anymore in if we do this, what would happen, but we are interested in the question, if we want this, what would we need to do? And that is what optimization is all about. And it has, of course, lots of applications in many fields. Wherever people simulate, you can also optimize. But there is a problem with it. And that is that most simulation software that is written nowadays is actually only intended for simulation. So people can actually play with parameters, and they have very convenient user interfaces for humans. But when you want to optimize, there's so much logic in these codes that you cannot easily formulate and also solve optimization problems. So what a lot of companies do is they provide some scripting tools on top of simulation codes, which basically do what an experienced engineer would do, play with different parameters, go through different inputs and so on. And always call automatically again and again, maybe in a parallel fashion, maybe on a cluster, the simulation model many, many times, so that you learn what would be for the given requirements the best output by just trying out. A bit like a simulation engineer would do by playing around. This is not what this course is about. So we are not, this is what we call black box optimization. Black box optimization is just copying this process of simulation with playing, it's automatic playing. Yeah, so black box optimization is one way. That is, so to say, automatic playing. Now you play with the parameters. But you can imagine, I mean, this sounds like a good idea. It's at least making your job easier as an engineer. If you have a simulation model, you don't need to go through all these scripts, or through all these steps of clicking and changing parameters and so on. It can really help you. But there is a problem. It consumes incredible amounts of computation time. That's why it's parallelized and so on. If you have only one parameter, it's easy. You just sweep through all the values of this parameter until you get the answer. If you have 2 or 3, you might still have some chance of just gridding it. Once you have more, 5, 10, 20, you already have a problem. And then people use some form of heuristics, randomized algorithms, genetic algorithms. You have lots of possibilities here. But they all suffer from the fact that your space in which you search is basically too big to explore it by sampling. And there is another way of doing optimization, which is much more related to numerical analysis, and that is what we want to teach you. And this is derivative-based optimization. So when we have spaces of dimensions of 100,000, 100,000, 10,000, or 10 million variables, so all these exist as decision variables, so things that you can change, then doing this by trial and error or even by automated scripting is completely impossible. I just want to tell you, think that you just want to try all corners in a hypercube, and this hypercube has the dimension 1000. Yeah? All corners in a hypercube of dimension 1000. You will never ever be able to explore all these corners. Yeah? It's 2 to the 1000 corners. Yeah? And this is, of course, not a very nice grid on a domain where you want to look at. So when you have the chance to compute derivatives of objective functions, and I will show you that computing derivatives can be done quite efficiently, then knowing where to go down in a high-dimensional landscape is already a very big gain, and that is what makes optimization fast. And it's not just a bit faster, but it's tremendously faster. So what we are looking at is, in some form or the other, we will always have to do with derivative-based optimization. So that is what we treat in this course. So maybe I make boxes around what we do. And we do optimization, and within optimization we do derivative-based optimization. That's what I want to teach you, because I think this is extremely powerful. And for me, discovering it was really revealing. I came from an application at a business consultancy at some point, did several weeks of work with an Excel solver that was implementing this black box optimization. So I could actually, in Excel sheets, specify I want to minimize that cell, and it's logically connected with these cells, and these cells the computers should modify within these bounds, and maybe there would be even constraints that should be respected. And then the Excel solver started to work for nights, several days and nights, and at the end we had a wonderful result. Somehow we thought at that time, but doing the same computations with a dedicated algorithm later, which I bought during this internship at this company, a consulting company, I realized that the same computations could be done with, I don't know what was the factor. It was so incredibly faster, because 10,000 of these problems could be solved in just clicking. Yeah, so I clicked, and then 10,000 of these optimization problems were solved, and they could plot a parameter study, not like in simulation, where you would also vary input parameters, but it was a parameter study for the objectives. So if I change some constraints, then I would get a different solution. And that's actually what we want at the end. We want to play again, like a simulation engineer plays with the inputs of a simulation code. In the end, what we want is that an optimization engineer plays with the requirements and looks, if I require this to be a bit more tight, this constraint, then the solution would look very differently. Or how does it look? And this is what you want to do. So it's not about replacing someone who did the simulation before by a script, but it's actually about making the person more powerful by playing with requirements and by playing with outputs instead of playing with inputs. So that's what optimization is about. Because I'm still in the process of exploring what is your background and your interest, I wanted to ask if someone had already some exposure with optimization in some form or the other. Also, black box optimization is absolutely fine. So if anyone ever called some optimization routine, I would be very curious to hear. So maybe first general survey. So who did ever call an optimization algorithm, like I did at this consultancy? So it's a significant enough number that I don't ask each of you to explain the details. But maybe among these who did black box optimization, okay, can you say, this is only one, so we get one example from black box optimization. Can you say, what did you optimize there and what did you
was the transport optimization problem where we have n trucks and package which you can load in the trucks and drive around in the country.
Okay.
And so it's a pickup and delivery problem.
Okay. A typical logistics problem. Yeah. So you had parcels, okay, you wanted them to travel and you didn't know which car should transport which parcel, more or less.
And it's also discrete, not
yes, yeah. I should say there is another dividing line which is completely complementary. There is discrete versus continuous optimization. And also for discrete optimization there exist not derivative-based but mathematics-based algorithms that can actually find global minima. And there is also black box optimization for that. This course is mostly focusing, I should say, on this part of the world, continuous optimization. But at some point you will discover some similarities to things in discrete optimization, or I will make some remarks to that field. So now the others, I suppose, are then all what maybe I should see. Did you work with derivative-based optimization in some form or the other? Or maybe can you give examples so who wants to present one optimization problem you solved sometime in your studies or somewhere else?
You mean black or just the general?
Anything. Any optimization problem you solved, preferably if it wasn't in one of my previous courses, I should say. Okay. So maybe that reduces the group significantly. So who solved an optimization problem but not in my class? Not you again, so someone else. Yeah, maybe you? Yeah?
Yeah, I was in the other university that optimization.
Okay, so you...
CG...
Okay, yeah. So the methods is one thing, and the other thing is the applications. I'm at the moment a bit more interested in which applications, but anyway. So you mentioned the CG method. CG. What application was it about? No concrete. Okay, so it was more a method course like what we hear. We had already one application that was parcels in trucks, let's say. Yeah. Other examples that you encountered.
Yeah, I'm trying to do impedance matching. So the application is impedance matching for microelectronics.
And you don't know yet which method, or did you try some already?
Well, what I try to do is to fit model parameters to a given function, transfer function, and I try to reduce the distance between some given measurements to this model and the decision variables then are the
okay. So you use least squares minimization. Yeah. That's a formulation actually of a problem, and then how do you solve it?
With
you can just say
and the theory point.
In which environment?
At MATLAB.
Okay, that's nice. Yeah, MATLAB, and then you use SQP method. We don't go into. We will learn about all these details later, right? Other problems you want to share with the group? Yeah. Sorry?
Training neural networks.
Training neural networks. That's for machine learning, right? Yeah. Training neural networks. And how do you do that? Which algorithms do you use for that?
Well, it's mostly backpropagation.
Backpropagation. I call it reverse AD. We will see later what this means. And on top of that, you use something like a gradient method, or maybe no, it's a different language in computer science, but it's probably a gradient method. Sorry?
Storage or pipeline?
No. Okay, the language is not what I wanted to ask. So, but it's basically going downhill, right, in a landscape. Yeah, that's a gradient method. Or do you use something like BFGS or no?
No, it's gradient.
Okay. Good. You don't use CG either? No. Okay. Anyway, it's just to get a bit of an idea. I don't want to throw some specific terms around. I just wanted to get a bit of an idea. I just wanted to summarize from my side that I think the big classes where optimization problems come from are actually already what you have mentioned here. On the one hand, these are, so to say, problems where you want to do something with the world, but you don't know yet what is the best thing to do. Yeah, so you have something like resource allocation in business, or you have some time optimization. Time minimization, cost or time minimization. So all these things is what you usually do in business or also in engineering. And then the other class, which I think is one of the biggest classes, where people have actually already done some data, they have recorded some things like a neural net, you have already some things that you would like your function to do. Also this impedance matching actually falls into this class. So you have some things that you want, and then you want to fit it to the fit, model fitting in some form or the other. And maybe this is even more common in applications. So if I remember when I once visited a mechanical engineering department, I was interviewing a lot of PhD students there that all were interested in optimization. Afterwards I concluded that 90% of all problems that I was confronted with during a 2-day visit, and I don't know how many talks with people, 90% of all of these problems would have been fitting the class of nonlinear least squares fitting. Yeah? So a lot of times you want to, a robot should follow a trajectory, or it should actually, you have measurements in it, you want that the model parameters are adapted to these measurements, and all these things are in the form of model fitting. And this is something that you have not only in engineering, but you have it also, I mean, you have it here everywhere, but you have it also very often in science. So several of my cooperations were also with scientists who just said, hey, we have these, for example, CO2 measurements around the world, and we have a model of how the CO2 evolves. Actually, in this case, it was not only CO2, but it was CO2 marked by atomic explosions. So there was a special radioactive CO2 in the Earth, and you could, using that, these markers that have been caused by American and French nuclear weapons tests, you could use them actually to detect how the flows of the upper atmosphere are in the world. And that was used to actually calibrate climate models. And then you had the same thing. You have a simulation model of the Earth. You have a lot of measurement data of how radioactive is the Earth, the air at different parts in time over, let's say, 10 years after these explosions. And then you want to use that information to estimate the flows of the atmosphere. So that was one of the, let's say, the biggest examples. If you think of what we try to optimize was the global system of weather. Even bigger is, of course, when you have to do with astronomic data fitting, but that also appears. So in science, this is also very popular. I think you are here. We know already what motivations we could have. From time to time on, we will talk again about interesting applications, but I think it's time that we also share what this course's duties are. Of course, I said already, the main thing is not to solve optimization problems, not to formulate and solve them, but the main aim of this course is to understand how they are solved. Yeah? So we will actually look into the numerics. Yeah? So the aim is understand the algorithms. And not only understanding, but we will actually understand them best if we even implement them. Algorithms. That's what this course is about. Yeah, so but of course you can never test an algorithm if you don't have an example. So from time to time we will have to look at non-trivial examples. At the beginning we start with very, very simple examples, you will see, and then at the very end we want to make the examples as complex as you can do it. And for this reason we have the following structure, and I want to explain to you what this course encompasses. So there are lots of different things here. So, this is nice. I should move that up. And I should ask the camera, is this still viable for the camera if I move it completely up? Okay, good. So we have the lecture. That is one part of the course, lecture. And this lecture is Tuesdays and Fridays. But accompanying it are exercises. And I would say they are equally important as the lecture, even though the lecture is 4 hours. And this is only 2 hours per semester. They belong together, and each week we will actually hand out an exercise sheet, which is very often on the computational side, and we will always use MATLAB for that. I will explain that in a minute together with Dimitris, who is our tutor for that. So we have the exercise, and we start next Wednesday with the exercise. But we also have something at the end of the semester. In March or so, there will be an exam, a written exam, just like in every other course. That is what is a requirement of the engineering faculty. I think in mathematics you might not even have exams usually, so you can maybe choose if you want to participate in the exam, but I would recommend it in general. Yeah? These 3 things are connected, and they are one part of the course which is in principle valid 6 ECTS. So that's one module that the engineers can choose. The mathematicians will also have it. That's what we all do. Everyone who is here and participates in the course will do this. Because these exercises will be more or less digesting the methods that we did already, and maybe guiding you towards implementing some of them, but not inspiring maybe as much as I like your creativity, we also introduced a project. And a project is something which comes after the exercises and which starts in January to February. So it's the last time. And the last time slots of the exercises will be empty, so there is no weekly exercise at some point, but at the same time we will start to work on projects. And this project is something that people can do from engineering and other subjects, and mathematicians will do. It will not change your weekly workload because it's exactly at the same times when you usually had your exercises, but it is something that we formally separated from the lecture so that we could make 2 program coordinators happy. On the one hand, the engineering program coordinator, which have lectures only of 6 ECTS, and then you can have projects. And in mathematics, we have a big lecture, which is at the end having a very practical part, a project. And about these projects, we will talk. Actually, we can start talking about them today. They should already now help you to get motivation or to get into touch with me and with Dimitris about what could be your project. So start thinking what would be an interesting project, but we can actually start talking really about it in a few weeks or months, I think. So it's not yet extremely acute, but what I could say is that the aim of the project is to do something which was not exactly like this taught at the lecture. So, for example, you could say, I have this, I don't know, this impedance matching problem. I have it. I want to try it to solve this problem with one of the algorithms that we have programmed in these exercises. But it happens that my problem has so many more variables that it's a bit more challenging, so I need to do some tricks here and there, and then we help you to get the right tricks. Yeah? Or training a neural network could be an equally nice project. So you make a small implementation of a neural network in MATLAB, maybe not the big thing that you have, but then you can compare different algorithms that we tested here in order to learn something for your field, which is that's the idea. So, and it can be anything. So in the past we had beautiful projects, and I love that. So I don't know, people had some things like one of my PhD students now, during the time he took this course, he had something like he wanted to compute the locations of electrical charges on some surfaces. So he said there would be 15 electrons on a sphere. How do they actually find their locations? Yeah, and if it's not a sphere, but something like an ellipsoid or something even in a different form, where do they find their locations? Usually they go somewhere to the boundaries, but they maximize the distance in a specific form, which is related to the potential energy of the electric field, electrostatics, for example. Yeah? Another project was where a person, let me think a bit, what projects did I find particularly easy to explain? That's the main problem of these projects. If I want to explain it in a second, I need to take the simplest ones, like how to maximize the surface of, you have a parameterized surface, maybe in 2 dimensions. You have a line, and you want to maximize the volume inside this line for a given length of the line, but you have constraints, like there's like something here where the line shouldn't touch, and here, and then some strange forms come out, which you could say is an optimization problem. These are more the mathematical ones. Then there were also, of course, more applied ones, like people said, well, I want to somehow find the minimum and the direction and the minimum speed that I need on a golf course, so that a ball moves up and finds the hole and then lands exactly in the hole. So that was heavily based on a good simulation model of the golf ball. It was only considering rolling motion in that case. But so that could be an optimization problem, which is much more on the modeling side, and some others are more on the algorithmic side. Given the fact that we are here in the mathematics faculty, and many of you are mathematicians, I also allow purely algorithmic projects where you say, I don't have a specific problem. I mean, I rather take, for example, a random collection of problems which I generate randomly, and then I want to test 3 algorithms against each other, and maybe one of them is even a new one. So that could be also a project. And the end of such a project will be a computer code that is usually in MATLAB. We could even make exceptions if you have nicer ideas. The second thing will be a small report, about 5 pages we have as a guideline, which looks like a small scientific paper, like a conference paper, you could think. And the other output is a public presentation in this room at the very last hour of this semester, where all the projects would be presented to each other, and we can ask questions about them. That's the fun part of it. Yeah. And this is after you gave the report, and the presentation can either contain even videos or demos, or it could just contain the contents of your report one after the other. So different ways to present. So that is the outline of how the course is organized. It basically consists of 2 things. This thing is what we all have to do. No one can actually do the project without having done the lecture. Formally, engineers can choose it, but I don't recommend it. So it's just something. So do both things together. And some people that say, no, in the second half of the semester I want to relax from January. I want only to listen to lectures and sometimes come and start studying for the exam. You could also, at least engineers and non-mathematicians could also say, I don't do the project. Because of this fact that we have altogether 9 ECTS, we will sometimes, it will be before Christmas maybe a relatively high workload, I would suggest. So besides these 6 hours that we have presence, expect maybe 2 hours homework, up to maybe 15 hours homework, depending on your background and what you need to do. I don't want to shock you, but I think this is realistic. In the worst case, it could go up to 15 hours. But I don't expect it. So expect something between 2 and 15 hours. Yeah. The question that was pressing me at the beginning is a very simple one. When should we start? We can start because we are in the afternoon. I guess there is no lecture before. I tested it here. The room was empty and even locked. So we could start at 2 o'clock, no problem. We could also start at 2:15. So let me just have a short vote or a picture what you think about the starting times. If someone cannot participate, if it's too early, for example, then we have already decided. So here's Tuesday, here's Friday. And here's the exercise on Wednesday. I want to understand what are the preferences, and the only things I can offer is this, 14, 14, or 14, 15. 14, 15. And for the exercises we also have limited choices. It can be 16, or it can be 16, 15. So I will go through each of these slots separately because it might be that some people have constraints. So let's just get a picture. Who wants, of course, it implies that we would stop a quarter of an hour earlier, right, if we start early. So the total teaching time is always 90 minutes. But what is here the preference on Tuesdays? So who would be in favor of starting at 2 o'clock? So please raise your hands clearly. 1, 2, 3, 4, 5, 6, 7. And who is in favor of starting at 2 o'clock 15? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think something like 14, and probably the rest isn't so decided. That's fine. I guess we would then go for 14, 15 if there's no strong objection against it from the others. Is there some very strong reason? No. Good. So we make this the starting time of the Tuesday slot. So the same for Friday or different? Maybe let's see. So who is today that we would have started at 2 o'clock? Would have been a preference for many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. 12 here, right? And who is for 2 o'clock and 15 minutes, like what we started today? 1, 2, 3, 4, 5, 6, 7, 8. And now the question is, of course, are there strong limitations because you have some lecture that just ends at 2 or something, or is it a soft? Could every one of these, because the majority is here on 14, would everyone live with that? Okay, so then we do 14, 2 o'clock. And then we have the exercise on Wednesday, which unfortunately is a slot which is at 4 to 6. It's a late evening slot, but I want to tell a bit about this exercise in a minute. So about the starting time, 4 o'clock. Who is for 4 o'clock? Means you can come home earlier also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think you also, I'm not so sure, but 11 I guess. And who is for starting at 16, 15? Okay, 1, 2, 3, 4, 5, 6, 7. It's nearly undecided, I would say. No, it's a bit less. But you raised your hand much faster than the others. So maybe are there strong reasons for starting later here? Yeah? You have? Okay, it's possible. It's not making it impossible to attend. Okay. Okay, even. So working. And you?
Me too. And until 12.
Okay. The good thing, let's say, about an exercise is that it's possible to sneak in a bit later because an exercise will not be a lecture in the same sense like we do it here. So maybe the tutor, I should also give a special vote. You can have 5 votes if you like.
Well, I can stay anyway a bit longer for the people that come in.
Okay.
Or you can ask if there is...
Okay. So we start at 4 o'clock. Yeah, maybe it's a good idea that I ask Dimitris to come to the front, so that you get a full introduction, also about the exercises. So my great pleasure to introduce Dimitris Chrysoupis for you. Dimitris is a Greek citizen who studied in Greece and in Switzerland control engineering and started his PhD 1 year ago with me, and his topic is optimization algorithms. So he's perfectly qualified for this lecture. And maybe you can say a few words about more about you if you like, or about the exercises if you like to say.
Well, okay, I have a background in engineering. I studied first electrical engineering in Greece, and then I went to ETH in Zurich for robotics and control systems before coming here. And about the course, so I'm responsible for the exercises. We're going to hand in the sheets every Friday. Moritz will maybe give some hints if they're difficult to someone, or even me if I'm here.
I will note these things while you talk. I mean,
you can also find them in the sheets, just repeat it a bit. And so the idea is that you should get familiar with the exercise before you come to the exercise session on Wednesday. You can even do it yourself if you want, and then you come there, and around me, maybe another tutor, and we help you continue with exercises. You can form groups up to 4 people, and so I have to be close to the microphone.
Yeah. I realized this is not.
It's big enough to loud enough.
Yeah. Maybe you better talk.
Okay. All right. So for the exercise, we have groups from 1 to 4 people. And I just put online, I think, a sheet where you can, I put the emails of the participants and the names that I have so far that are registered in this HIS system. Probably people from the mathematics are not registered there, so just put your name after and so on, and with your data. And then you can form groups there. If you don't know someone, you can just send an email to someone and ask, it's pretty straightforward. Just have a look at the sheet and put your data. And so hopefully most of the teams can finish the work even at the end of the exercise session. I can just check your results, give you the points, and you go home. And if you need more time, you have until Friday to send me an email with your solutions. And as it's written in the sheet, you need 40% of the total points of all exercises in order to be able to give the exam. And if there are any questions, you can always ask me or send me an email or anything you want. So,
okay.
To you.
Yeah, I just wanted to summarize. I had written down what Dimitris just explained to you. So the timeline is on a Friday you will get a sheet. Then on the weekend you can already look at it. I will also say a few words, or Dimitris and I will explain a few words. We will do that immediately, actually after break. We will actually work on the exercises on Wednesday together, and in the best case, when everything works fine, you just raise your hand at some point and you say, Dimitris, please have a look. I did this and this and this, and then you agree on how many points you get. If you did all the exercises, you get 10, and if you did arrive to somewhere, you say maybe 8, and then you can be happy. And then you can forget about exercise. It's for you. It's not for an end mark. It will not count for the end mark, right? So the grade will be based only on the exam and on the project. So this is 2/3 and this is 1/3 according to ECTS point. So you can completely relax on not having the full amount of points. Yeah? We want to have it a light procedure. You should understand and have fun. Yeah? If you cannot participate on the exercise, you could actually hand it in, or if you didn't finish and you need more time, you can still wait and send the full responses by email in form of MATLAB scripts or some scanned handwritten notes and so on to Dimitris.
Okay, and
you agree on that?
So since we're in the questions mode, I was wondering who you have already experience with MATLAB before? Okay, that's very good. So the thing is, the exercise takes place in a normal hall, whatever, without. It's not a computer pool, so we won't have computers there. So please bring your laptop, or one person of the team at least should have a laptop. And of course, by Wednesday, try to have already MATLAB installed on your computer. It's for free. I put a link on the exercise sheet on how to get it. probably you know about it already. And yeah, the sheets, you can also find them online together with material for the templates for the exercise and so on. Right. That's it.
Okay. So that's about the organization. Actually, you didn't ask one question, which I still want to ask. Who did never use MATLAB before? It's also possible. It's absolutely possible. So what I would suggest is, because we have these groups possibilities, that you try to find a partner who knows already MATLAB and learn a bit during the exercise sessions. In the sheet we also point out some tutorials how to learn it. MATLAB is a very intuitive language. And all students of Baden-Württemberg have the right to install it on their computers, so you have all of MATLAB, all the packages that you need, everything is there. The only thing is you have to install. The other question I have to ask is, does everyone have a laptop or knows someone in the same lecture who has a laptop with whom you could work together? So in case, I look into your faces, so are there many people without a laptop? No? Okay, but you would have some way to find someone with a laptop to do the exercise together? Yeah, that's very recommended. We, in the past, let's say, I usually did exercise in computer pools, but increasingly it became much more convenient that people bring their laptops, and the simple reason for this is that if you do something on your laptop, you didn't finish, you can just do it at home and continue with the same working environment. That's why it's so convenient. Okay, so that's what I wanted to say on the technical side. And about the organization of these lectures, I will usually have a break of about 10 minutes. 10 minutes is a typical good duration for a break in the middle of the lecture, and I suggest to have the break now. What we will do after the break is I want to share a bit of motivational videos with you. I want to give already a little bit of theory today, and then go already through the exercise sheet. So that's the topic that we will still do in the second part of this lecture. But now I wish you first a short break of 7 minutes, and we come back at 3:15, I suggest. Yeah? The main communication that we have with you, apart from being in the lectures and in the exercises, is via the internet. We have a page which is here found on the syscop.de. And on this page we will actually locate in particular the exercises, so you can actually find the exercises here. General information and introduction to YAML that we just distributed. But you can also find literature links, and in particular one script that we continue to write during this time of the exercise, of the lecture, which are some lecture notes on numerical optimization, which contain basically everything that we will do on the blackboard and a bit more, possibly. Sometimes a bit less. Yeah, so there is some freedom, but I try to at least keep the numbering and so on consistent with the script. If you see the script now, it's not yet in a perfect state. It is having most of the contents already, but not in exactly the same order that I want to present it here, and I want to add a bit later. But the first part is already more or less finished. And so if you want to print it out, you could just print out the first 2 or 3 chapters and then wait. And what we will do in the meantime, in about 1 month, I will release a more or less ready script, and then I will ask those of you that are interested to get a printed copy, and then we print out copies for you for free. So that's an extra offer. Then it looks like a little booklet. So this is already a way to directly tell you what this course will be about. The course will be divided into 4 parts. And the first part we start today, and in the next week, it's about fundamental concepts of optimization. The next part is unconstrained optimization in Newton-type algorithms. So it introduces a lot of the of the algorithmic ingredients already in the simplest possible setting, which is unconstrained optimization problems that don't have any constraints. And then the next two parts are about equality constrained optimization problems. That's the next more complex class. We will deal with Lagrange multipliers and so on, and many algorithmic details will be discussed there. And this part, by the way, is new, and I will move some part from the other parts into that one. So that's completely empty at the moment in the current script. And inequality constrained optimization is the more complicated way of constraints that we will treat in the last part. So yeah, this is the most important thing about the contents, and what we will do today and tomorrow is a bit about fundamental concepts, and on next week we will go through classes of optimization problems. At the beginning I want you to have an overview of what optimization problems exist and how do people call them before we learn actually to solve some of them. I will also give a special focus on a field that's called convex optimization, which could be covered by complete courses, but we do this in one chapter, which will comprise about 1 week. We will also mention duality and explain and prove some little theorems here. And then it becomes really algorithmic. We go through different classes of problems which have different algorithms, like fitting problems. Newton type optimization is a general class of methods. There are many details, and globalization strategies are one of them. I will tell you later what it means. But calculating derivatives is something you already understand now. But I hope that it will also surprise you, like it did surprise me when realizing that this is a mathematical field where a lot of applied mathematicians really spend a lot of brain power and know how to compute derivatives as efficiently as possible. And that means not learning rules which make it more efficient to compute them on hand, but it's about complexity of how to get derivatives efficiently. And one of the highlight results I can already tell you is if you have a simulation code which has millions of inputs and gives you the answer of some objective function after, let's say, 10 minutes of computing time, then you can, in principle, compute the whole gradient. That means the derivative of this objective function with respect to 1 million entries in about 40 minutes, even though you have 1 million numbers to compute instead of one. And that is due to a very efficient way of managing storage and of actually going through the code. So calculating derivatives is a science of itself, and we will at that time even learn to use new computing tools which are all implemented in MATLAB. And the rest I will not explain now. You can go through the table of contents if you like, but I mentioned already that there are 2 more parts. Okay, so that's everything I wanted to say on the script. So don't print it out. It's a preliminary draft, but if you want, you can print out a few pages. One other thing which I had to mention, and Dimitris reminded me that I should not forget it, is that there are 2 things that are still important. And one is completely administration-wise. So we have created this project as a separate quantity for the engineers and for the computer scientists. So you remember we had this project and we have the lecture. It was only created today. So most engineers are subscribed to the lecture, and computer scientists, but please also subscribe in this system HIS-in-One to the project. You can still later unsubscribe, but just please, if you are here, subscribe if you have any intention to do the project. That's the first thing. The mathematicians will be automatically registered to both systems, but as far as I understand, because I didn't see any mathematician yet in the system, either it doesn't work yet for you or you just didn't bother. But if you know about HIS-in-One, maybe you can try once after the lecture to register. And if it doesn't work, you iterate with Dimitris of how you can be registered. And if it all doesn't work, then we can register you by hand. You just tell us the matriculation number and the name, and then we just put you in. There are many possibilities. But at the end of this month, we should have registered everyone so that we satisfy all the formal ingredients. Yes?
just something I remember, because when you're creating a web page from an old one to the new one, make sure you put the www in front, and sometimes the old
Yes,
one here
yes,
that
yes.
doesn't have the code, so make sure you use it.
Yeah, so you see, please don't forget the www is coming, because at the moment we have 3 web pages for the group. It's completely crazy. But that will be the new one, and you work on the newest one. Okay. Yeah, now that I'm here on the computer screen, I think I will directly use it to also do a bit of motivation. And I think I just wanted to share one simple thing with you, which is about optimizing in a very, no, it wasn't this tool I wanted to call, in a very high-dimensional space. It's this tool. Yeah, exactly. And I wanted to just give you 1 or 2 videos that could be interesting. So why would we want to do optimization? And the first example I want to share with you is optimization of mechanical structures. It's something that people use to... sorry. No. I will first repeat the story that we did already before. Namely that we have simulation everywhere. It's the story that I already outlined to you, that we usually play with input parameters. And the question is if the computer can't directly optimize, and that's what we want to do. And so at the end we want that the engineer plays with with output parameters like the objective and constraints. Of course, this course is designed to have optimization methods at their core, but we also want to connect them with applications to give you some feeling of what applications could be interesting. And actually it is of interest for method developers, because you will learn what methods would be needed by people that use optimization software if you want ever to become someone who develops tools. On the other hand, as a user of optimization, you could actually profit from having smart ways to formulate your problem and use the right algorithms. So that's the added value for people on the application side. The optimization of mechanical structures is the first example that I want to tell you. So this is something which is probably not what we do here in most of the faculties in Freiburg. It's mechanical engineering, and it's even civil engineering, building bridges, roofs, or even aircraft wings. So the typical task there is that you want to minimize the material usage of something. So you want to build a bridge, but it should not be very heavy, so should not contain a lot of steel. But at the same time, you want that this bridge is stiff enough to hold everything that you want. Yeah? So you see roof structures like this one here. There are all these parameters of how thick should each beam be, so that it is stiff enough, but at the end you want it to be very light. And you see some beams are much stiffer than others. And you can imagine that instead of just trying out these things and then simulate them with a finite element code and seeing if it all works out, you could also say, let's just say the diameters of all these things are optimization variables, please play with them. Yeah? And that is what people do. I like this example that you see here on the left side. That's a quite impressive example of 3D optimization of a structure. And here you do something that sounds like completely crazy. You say, I take a 3D, like a tomographic image of some block, and you have these voxels, yeah, 3D equivalent of pixels, and each voxel could have material or not material. Actually, because convex or continuous optimization is so much easier than discrete, you actually say a voxel could contain no material, a bit of material, more material, or full material. So you have a relaxation between 0 and 1 material, and then you have some other ways that try to avoid non-integer materials. But then you start your algorithm to optimize, for example, so minimize the amount of material that you have, the weight, but still you want that it supports something like a camera weight. Think of this thing that we have here at the back. That's a camera support, so it should hold a weight of something. And this is a constraint actually, because it would buckle if it doesn't have enough material. And then you start an optimization algorithm, in this case a very high-dimensional one, that starts to modify all the contents of all these voxels and guides in this very high-dimensional landscape, guides you through until it finds hopefully a local minimum. It will not be guaranteed to be a global one in this case, it's impossible. But the surprising thing, which I find extremely beautiful at these problems, is that at the end you just say, the inputs were a model of your material and where the force enters, and that you want to minimize material, and the output is the structure that we see here on the bottom right, which is somehow like magic appearing, something that makes sense from an engineering perspective. So that's, I would say, one of the most beautiful applications of optimization algorithms. That's why I wanted to start with it. And it is also used in practice with free material optimization, that is called. In, for example, the aircraft section of the, this is an aircraft section, this is an aircraft section of some aircraft, I don't know. But I know that I forgot that actually because this is an old slide. But what I know that is that in the wing of the A380, and I don't have the picture here, sorry, that there is this part, I mean, if you have a big airplane, this part of the wing, the shoulder, so to say, is the most loaded one. That's the most difficult part of an airplane wing, because the whole lever arm of this big wing acts on this part. So the construction of that part, let's say a few meters from the main body of the aircraft, the fuselage, to the wing, this is like the most crucial element of the wing. And so that's where a lot of engineering effort is spent in order to make that efficient and stiff. And people used topology optimization to minimize the weight of that part and maximize its strength. And what you get out is very organic structures, so it's beautiful. And I will try to find that picture to the next lecture. It's somewhere on the way. I want to show you how such an algorithm works if you just run it. Where did I have it? I think we have it here. So here you have a typical task. So this is the end result already. So a typical task here is that you have a block of material, you have pixels. In this case it's a simple thing, it's a 2x2. I think it's about 20 or 30 pixels in the upper direction and maybe 150 in this direction. And each pixel can be something between 0 and 1, and 1 means very stiff and it also weighs, and 0 means there is just air. And then you start with a full block, but you start also with a specification that you have a load at the top, some force that presses there, and then you have some supporting points here, and here that support this material. And then you start the optimization. You start usually with a gray block, and then the optimizer goes downhill in a very high dimensional landscape, and after the convergence, which might be nearly as fast as this one. This is a video, so I don't, it's a bit slower, but at the end you found a local minimum and you found a minimum in this very high dimensional landscape. So it's something surprising, I would say, and think of how you would do that by playing with 0 ones in this domain. It's impossible, right? So going downhill and having derivatives is really making these things possible, and only because of the fact that we can look into these models. It's not black box models, we need to have the model in an optimization environment, otherwise we could not do it. I wanted to present some other topics, and I will not go through one of my favorite ones yet, I will do that later. But just show some videos that some people have seen already from the lectures of optimal control. But if you want to optimize the motion of some body, then you have a so-called optimal control problem, and here the decision variables are commands, inputs of a dynamic system. It's like when you drive a car, you could decide at every second which angle should your car wheel have, or which how far do you press the gas pedal. And if you want to optimize the motion of a car over, let's say, 20 seconds, you could make all these decisions, one decision variable, and then you have a very high dimensional optimization problem. In motions of a crane. This is a crane, there hangs a load at the bottom, there's a motor at the top, and the aim would just be to move it from one position to another one and not have it oscillate at the end. So the decision variables here are actually the speeds of the slider at the top. You can move these speeds, actually the acceleration is what you can really influence. And you influence it, in this case, over a horizon which has a variable duration. And you want to arrive as fast as possible at the point where you want to be. That is the task here. And in this case, an operator says, now I'm here, but now I want to be there, and then maybe I want to be there. And then you start this, these optimal motions, and the result would then look like this. So you see the influence is at the top, and at the bottom is what we want. So you move it somehow, it's a bit strange, and a human being wouldn't move it like that. But that way makes sure that you land exactly at 0, and you do it in a time optimal fashion. So that is what optimization can do for control. This was done in the mechanical engineering department, and I like these applications because they are very visual. And here's another time optimal motion for a robot that writes Optec. Optec was an optimization and engineering center, or is, that exists in Leuven. And where I worked for these 8 years. And this was a motion where the robot would actually be very fast when it can afford to, and get a bit slower when it approaches a curve. And so it's really optimizing also for time here. So it just tries to be as fast as possible. Here you could say something that is more like in the direction of artificial intelligence. You would say a robot has some recognition system. It recognizes that there is a box, and if you have this box, then you need to plan a path which avoids that you touch this box. So you have something that we call constraints that should not be violated. I skipped that one, I think. But this one I also like because it's quite impressive. This is the same crane that we had at the beginning. It is something where you have a mouse where you can write something. It's virtual writing, so it's not written anywhere. It's just written on a computer and moved into this video. But afterwards, what you see, what the crane does, it follows this, what you wrote, even though, of course, you cannot control the location of this ball. It's completely based on a forward simulation model that is then inverted by an optimization algorithm, and it will do in a time optimal fashion what you wrote. So you wrote something, and then it moves along this path as fast as possible. Oh, here you see there was an error. So that sometimes happens here. Very rarely, I think that's the only error in this video. But this is what you can do once you have a good simulation model and a good optimization algorithm and a good experimental setup, I should say. So these are the possibilities, what people can do and what people do with optimization. Here I should say that now that you have this waiting time of about 2 or 3 seconds, this is the time when the computer actually optimizes. So it computes the orbit that is then afterwards just demonstrated. So it takes only a few seconds to compute these orbits, these optimum motions, and then it's doing that. Are the race cars? Yeah, something that is now at the moment presented by Robin, the student whose feet you see here, at Rust. So for kids, it's a fun project, but what we do there is we observe a car from the top, and then it should also move as fast as possible along a track, and we are still in the process of making our prediction models better so that the thing can become faster. But here you see some preliminary results of the black car, which is actually not his car, it's the automatically controlled one, which is getting quite fast already. I should say that there are even faster cars that are optimized for speed. Okay, so that's it. I think I will leave it with this for the applications. And instead of doing now already a part of the lecture, I think it's more important that we go through the exercise sheet.
It's in a zip together with the templates that you just want.
Ah, okay.
Yeah.
So is it like this?
Just download it.
Okay, so if you download this, you will get a lot of things from Dimitris. He made your life easy. You will get MATLAB files and a PDF. The PDF is what you got also on paper, and which I want to go through now. So, what we want you to do here is actually to formulate and solve an optimization problem without knowing about the algorithm. So this is just as a user of an advanced tool, and later on we will understand much more what is happening inside this tool. This tool is called YALMIP. It's based on MATLAB, and YALMIP is a strange name for this tool. I don't explain it, but it's easy to remember what YALMIP is, and it's a really useful and nice environment. So what you have to do is you have to first prepare your laptop. That means first of all install MATLAB. You can get instructions from the Rechenzentrum. I will not show that. There are also some useful tutorials that help those that don't know MATLAB how to get started with it. And then the second thing is you will install YALMIP. YALMIP comes for free. It's developed by Johan Lefberg, a professor in Linköping University in Sweden. And it's a convenient way to formulate and solve optimization problems. So you need to install it and go through a few commands here. And then you test it by basically calling YALMIP test. And if that gives you nice plots and results, then you're happy. Yeah? And then you're ready to start the real exercise. And after you can start, and I should say you should have done this before you come on Wednesday. Because it will maybe take no time, but it will maybe take 3 hours on your specific computer to install a software. You never know, right? You know these difficulties. So please make sure that you have the software on your computer or the computer of your one friend of you who agreed that you work together. Yeah? So you have it on your computer, and then we go through the exercise tasks, and they actually are best explained. I think I need to already give a bit of theory, and I will do it. We formulate a simple optimization problem and solve it once on paper. That's extremely easy here. It's just a starter, minimizing a quadratic function minus 2x. It's school mathematics, you will be able to do it. But you then should solve the same thing with YALMIP. And that's, of course, just to learn how to use the YALMIP. And then we change something which we call inequality constraints. And then you should solve this again and say what is the answer. Now, this is already a two-dimensional optimization problem. Later on, as you know, we will have many more parameters, like thousands. But to give you already a bit of the spirit of higher dimensional optimization, we will then compute the equilibrium position for a hanging chain. So what we assume here is that we have a chain of masses. So think of balls connected with each other with springs, elastic springs. And these balls form a chain when you hold them on both sides. And what makes it interesting is not actually that it will find a very beautiful geometrical shape by minimizing the potential energy, which is a mix of gravitational energy and spring potential energy. But what happens when you actually add a constraint that the balls, for example, should not or cannot fall down off the ground? Yeah? So when you have this chain of masses and you make it so that it is close enough to a table, it will actually hang, at some balls will touch the ground, and then the rest of the chain will go up again. And if you have actually two types of ground, then it will somehow mold in it and some parts will hang, but which parts are in the air and which parts touch the ground, that's something that you wouldn't know so easily, but optimization can easily show you. So this is a way to get a bit of a feeling of what you can do with optimization and with YALMIP. And later on we will use this chain example also for testing some of our algorithms. Okay, that's a starter to get familiar with MATLAB and YALMIP and with optimization in general. And this exercise sheet you can already read, and then on Wednesday I would recommend that you come there, do the exercise, and if you're done in an hour, you are happy and you go home, and everything is done. Okay? Yeah. Let me now start with a little bit of theory before we stop. And this is not on the computer screen anymore, so maybe it's better that we switch on the light again. And I just wanted to jump into the first chapter. We did already a lot of parts of the first chapter, but I want to make sure that we know what we talk about when we do this first exercise. And so we are in the part on fundamental concepts and of optimization. And this section is about the mathematical formulation. And what you have seen already is that an optimization problem consists of several ingredients. I mean, the first thing that we always think of is an objective function, right? So we have some function f, but it will be a function of some parameters. And that is the function that we call the objective. But the objective function must be a function from some decision variables to the real numbers. So this f is the objective function, but we have decision variables, the things that we can change, and they are what we denote by x. And very often we assume that these decision variables are real valued vectors in Rn. For me, a vector is always a standing vector in this lecture. So it consists of n components ordered on top of each other. And then the objective function is a function f, which is then, if Rn is our decision variables, a function from R to Rn to R. Now we have to write somehow min or minimize. Both are possible notations. In the field of optimization, we very often indicate which variables you minimize over. So you would actually state this statement here. So we indicate them in particular here, which set we optimize above. So with this, we would already have an unconstrained optimization problem. We have some function that we want to minimize. We have decision variables. But then you typically also specify things that you want to do. For example, this robot that should end at a certain, this chain, the crane that you move from one position to the other. At the very end of the motion, the crane should exactly be at some position, namely at this endpoint without any oscillation. And this is a constraint. And these constraints we express with using the word subject to. And then we list all the constraints of the optimization problem, and they are functions or functional requirements that our solution should satisfy. So we have, for example, something that should be 0, some function of our decision variables that should be 0, or, and I stick to the same notation as in the script, you could have some functions that should be bigger than 0. So, for example, you don't want to violate some constraints. And by adding minus signs and subtracting and adding numbers, you can always bring them into this form. That's why we have this standard form. And what we have here are equality constraints. And they are characterized by this function g, which is a function from Rn to, and let me use the same notation, Rp. Okay? So that means that all components of this function should be 0. There could be many components. It need not be one single function, it's several functions. So this g itself is g of x consists of several components. g1 of x up to gp of x. And all components should be equal to 0. And now the same is actually for the inequality constraints. So we write it down like this, inequality constraints. And these are functions h from Rn to Rq, just to use the same notation. And what we mean here is actually that h1 of x should be bigger than 0 up to hq of x, that should be equal to 0, and all these equalities should hold at the same time. So that is a component-wise inequality. So when I write it for a vector, so then there is a vector here and a vector here, but I mean that it holds for every component. Yeah, that's not customary for equalities. We are used to it. I mean, that's making sense. This is typical and for optimization, that is component-wise. Each component. Okay, and all these things together, the specification of the decision variables, of the objective function, of the equality constraints, of the inequality constraints, they constitute an optimization problem. Very often I will make boxes around optimization problems in order to make sure that we know what belongs to it and what doesn't belong to it. And of course, this is a very abstract statement, but we can have concrete statements of optimization problems, and that's what we will have in these exercises all the time. I just want to have one two-dimensional example so that you get a bit of feeling what I mean with all these functions. So I could have, for example, an optimization problem where I want to minimize. I abbreviate it now. I say x is element in R2. I have a two-dimensional problem, and my function is the objective function is the sum of the squares of the two elements. So when we look at this function in the space of x1 and x2, then it has level sets. We will define them, which are like this. So this is where the function is 0, and then it grows at the boundaries. So you can think of this, it's a paraboloid going up here. That's the objective function. Then we have constraints. Let me just add one constraint first. This is the constraint that says x2, I just invent some numbers, -1 minus x1 squared is bigger than 0. Okay, this is a bit not so easy to read, but maybe it's nicer to read it if we bring these things to that side. Then we see that it's equivalent to x2 being bigger than 1 plus x1 squared. That's just a different statement of the same constraint. And this is to just bring it into this form, so that would be the first inequality constraint, right? But this one is maybe how you would write it in a language and say it, and also YALMIP would allow you to write it this way. But what we will now do is we will look what would be the feasible points. So this function here is this function, right? That's the quadratic function of x1. Sorry, here is x1. And x2 should be bigger than that. And so everything that is below this is forbidden. And I will denote forbidden parts when I illustrate things with these stripes. So this is where you should be, that is allowed. And so now you see already that the minimizer of the objective function is not a feasible point, it's not allowed to be there. So we actually need to look into a subset. And we will also include another constraint, which is this x1 minus 1, which should be bigger than 0. X1 should be bigger than 1, it means. So here we have 1. Here we had also 1. And this constraint basically says everything here is forbidden. And the only points that are remaining that we are allowed to visit are these ones, this and this, because both inequalities should hold. And what we call the set of points which are allowed, we call it the feasible set. So it's the set of feasible points. And I think this is enough for today. we have an idea of what an optimization problem is, and we have a rough idea of how to name the objects that we need to formulate. And with this very basic knowledge, without any more mathematical definitions yet, I want to encourage you, so to say, already to think about these Hjalmar exercises and get an idea, maybe just to see the optimal solution here would be obviously this point, right? If someone likes, you can also use that test problem once in Hjalmar and just see that it does what you expect. This is all for today. I'm looking forward to spending more time with you, and in particular doing also the exercises. I will join Dimitris on many of these exercises because I'm also interested to see how you do them and how it works. But next time we see on Tuesday, and at which time was it? Tuesday at 14:15, and Friday we always meet at 2 o'clock, right? So that was the point. So 2:15 on Tuesday. Let's meet again. See you. Bye.